This conference will now be recorded.
Okay, Glenn. Have a good one. Thanks.
Okay. Hey, Gil. How you doing? Okay, folks, we're going to start. This is Glenn Broderick, and I'm with Vitrek, and right now I'm in Orange County. And today we're going to take a look at the DL series electronic load. And this is an exciting new technology. There's really nothing like it on the market. It's been architected totally differently from anything you've seen before. And so I'm going to cut to the chase real quickly. I'm going to skip everything that's not essential, and I'm going to go right into a demo and show you how the load works. And I hope that helps. There is a chat button up above. If you have any questions, feel free to chat to me. Otherwise, if you could mute your mic, that would probably be a good idea. Bob Morrill, if you could mute your mic, that's probably for the best. Thank you, sir. And So today we have Chad Clark and Bob D'Amico with us as well. Chad is the Vice President of Sales for Vitrek, and Bob covers the Eastern region. I cover the Western region. So feel free to contact us at any point if you have any questions. Normally about this point we show the marketing slides and tell you about what we do. We show you all the different markets, but we're going to go directly into the load today. So to begin with, what is a DC load? I know you guys know this, but just in case, it's a test instrument to sink current and absorb power from a power source. Okay, so loads typically can be constant current or constant voltage. Again, this is a new type of system, and we also have the ability to do constant power and constant resistance. So you'll see the picture of the load. That's the front panel on the right, upper right, and then you see the back panel on the center. What's unusual about this load is it can go down to 0 volts DC. And why that's important is because a lot of people are doing semiconductor work, and the semiconductors are running lower and lower voltages. And so it's very hard to test when you start getting below 2 volts or 1 volt. We can go down to 0 volts. We can also go up to 500 volts DC. So, that's a little unusual. You don't see that near as often. Photovoltaics. If you're doing any of the modern photovoltaics, they can operate at a real low voltage, but very high current, and that's where our type of load comes into place. So the other thing we can do is real world simulation. So a lot of times in the old days, instead of using a load, we'd actually use some product, maybe a light bulb as an example, as the load, or a motor as the load. But the problem is repeatability. You don't have the repeatability with that, and perhaps the accuracy of the measurement. I'm going to show you how we can do real world simulation using this load that's completely repeatable. Notice that we have a color touch screen on the front. That adds a lot of capability. There's a lot of things we can do. This is actually about a 4-in-1 instrument. It's a load, obviously, but it's also an oscilloscope. It's also a data logger, and it is a high-end multimeter as well. So not only a high-end multimeter, it's monitoring all the parameters, 4 parameters simultaneously. It's like 4 multimeters in a way. Because we can put this on a web browser, that also means we can put up on a large monitor. So the color touch screen on the front is nice, but I like to put up on a large monitor because I can remote into this. And what that allows me to do is I can monitor the test from my office without ever going out into the lab. And it means that I can actually start the test and stop the test remotely from anywhere in the world. Now, this load, among other unusual characteristics, is its ability to change really rapidly. And we're going to talk more about that as we go forward. So right now, there's 6 models available. They come in 125 watt, 250 watt, and 500 watt, and also 0 to 150 volts or 500 volts DC. But as you go forward, you're going to see that that 500 watt load may replace a 2 kilowatt load as an example, or a 1 kilowatt load. I'm going to show you why. So color touchscreen, lots more capability, 4-in-1 instrument, meters, oscilloscopes, data logger, and we have a unique design that is proprietary to Vitrek, and that is our no ranging design. And what that means is in the middle of your test, other loads have to change ranges to cover the wide dynamic range. We don't do that. We can handle it all with one range. And that allows us to go down and be a load for small signals down to microwatts and really large signals up to kilowatts. And so we'll talk about that more. The load accuracy is the best in the class at 0.05%. Now, why is that important? Well, you're going to measure how your device performs, and if your load is off, if it's low or high, that's going to affect your measurements on your actual device. So having a more accurate load enables you to make more accurate measurements. This accuracy is typically 10 times better at low loading levels. We're especially good at low loading levels, and it's usually about twice as good at higher loading levels. Now, in addition to load accuracy, we've got nice meters in here with a 0.03% accuracy and 5-digit resolution. And what that allows you to do is maybe you won't need another external multimeter or several multimeters. Maybe it frees up an oscilloscope for other tests. Maybe it gives you a data logger that you wouldn't normally need. So all because of the unusual architecture of this load, we have a lot of extra capability. Now, the touchscreen, it also makes it a lot easier. If you've looked at old loads, you know, they have some pretty primitive displays on them. You know, they'll display voltage or current and maybe not much else. But having a color touchscreen not only displays a lot more, but makes it a lot easier to set up and control. So fastest load on the market, we can change load in 20 microseconds. So, and we'll talk about that more. High-speed loading changes to 100 kilohertz. Why would you want that? Well, a lot of people use these loads for things like checking the regulation of a power supply. And it's one thing if the load's changing slowly, you know, a lot of power supplies can handle that. But the question is, as that load change goes faster and faster and faster, how well do you dynamically regulate that? We can test that with this, where you wouldn't be able to do that with other loads. We have a special battery test mode in this, and it's because we have a data logger as well. We can test your batteries and log the data and do it down to 0.05% accuracy. This system, because we are a non-ranging design, we're better at large crest factor signals. So what is a crest factor? Typically, you see sine waves coming through, and those are easy. Most systems are designed to handle sine waves, but a high crest factor signal is one that is spiky. It has large peaks and a low average voltage or power. Because we have one range, we can handle that high peak, and then at the lower levels, we can still make accurate measurements, all again with one range. So we can remotely control this. We have a web app on the unit, and I'm going to show that to you in the demo. We can go down to 0 volts, I said, but we can also go up to 84 amps sustained current or higher. And I'm going to tell you about higher. This is American made. We design it and we manufacture it and we support it out of Poway, California. That's a suburb right next to San Diego, California. So what do you use a load for? A lot of times you'll see it used we've discussed how it can be used for checking the regulation of power supplies. It can also be used to emulate LED drivers. So a lot of our customers make lighting. In the old days, it was fluorescent lights, and then it became LEDs. And so when you test an LED, an LED has a driver that goes to it. And you can have many drivers, but the problem is they're not necessarily very repeatable. This load can emulate the drivers for testing LEDs. And it can also be used for testing UPS, uninterruptible power systems, inverters, DC to DC converters, photovoltaics, a lot of batteries, fuel cells, semiconductors. Semiconductors tend to operate at lower voltages, and because of that, this is the perfect load for that type of work. Now, here's a real life application story. This is a company that made the electric drills here, battery powered drills. And those battery packs get used for other appliances as well. It's not just drills. And so, you can use the drill as a load as an example, but having, 50 drills around for testing is not very good. And it's not very repeatable because drills can vary from product to product. So again, we can emulate that drill by using an arbitrary mode so that we can, for instance, you squeeze that trigger in that drill, squeeze it 10%, you draw a certain amount of current, squeeze it 70%, you draw another, and 90%. So voltage and current are ramping up and ramping down all the time. Now, if you have a really good battery program, you charge the battery all the way up. Lithium ions really like that, and charge it all the way down. And if you do that, you'll get the most capacity out of the battery and the longest life. But who does that with a drill, right? I mean, do you really charge your drill all the way up and discharge all the way down? So what we can do is simulate the customer experience by having it ramp up and ramp down in arbitrary methods to emulate, actual work. We can calculate the total watt hours, and we can calculate the battery capacity, including for brushless motor efficiencies. Now here's a nice curve, and I think this drives in why the high dynamic range of the system is unusual. This is a typical competitor's curve. We are looking at current on the vertical axis. We are looking at voltage on the horizontal axis. And so this is where they can operate, okay? So notice it can't go down below probably about 3 volts. We can go down to 0 volts. And so if you look at the area under the curve for them and the area under the curve for us, you can see that ours is useful in over a much wider range. Now, we also have specs if you're going to have a current transient. Let's say it's only going to be 100 microseconds, then you can operate within this red curve. If it's only going to be 1 millisecond, then you can operate within the orange curve. So what happens is a lot of people get these transients, and so instead of buying a 500 watt load, they buy a 2 kilowatt load because they don't want to blow up their load. Ours is actually designed to take these transients and go way beyond its normal operating range, which is here. So this is a picture of the front panel. That's the LCD screen and touch panel. We have an adjustment dial, which is handy for moving cursors and so forth. We have USB, and this is the front panel banana jacks. Notice it says it can do 500 volts peak and 30 amps RMS. For higher currents, we have a couple of jacks on the back, so that's the limit here, but obviously we can go to much higher currents. Matter of fact, on this, I'm just looking at this, we're showing over 110, 120 amps of current right here on that curve. So let's see. This is the back panel, and we give you a spot for a ground. Notice that we are using 12 volt 2 amp, basically a laptop charger to drive the unit. The advantage of that is that test equipment, the most high failure item in a piece of test equipment is the power supply. And it's a shame if the power supply dies that you have to stop your testing and send your unit back for repair. With us, all you have to do is plug in a laptop power supply. And it's not very hard to find something that's 12 volt 2 amps. You can probably find something like that around your house or your business to begin with. Now, we have the ability, about 2-wire and 4-wire measurements. it turns out that if you use a 4-wire measurement, you sense the voltage directly at the test article, and that allows you to ignore the voltage drop across the leads. So as current goes up, there's more voltage drop across the leads, and we can do 4-wire loading. We basically run the wires up to the test article, and so you can ignore the lead. Here's our Ethernet port, and we have digital I/O. Digital I/O is for remotely starting or stopping the unit or triggering the oscilloscope, that type of thing. So I said that our accuracy is 0.05%. Would you believe that means we're about 10 times better than most other units at low loading levels? And we're usually about twice as good at higher loading levels. Now, the LCD screen, okay, here is, here's our slew rates. I said that we're very fast. We can actually have a slew rate of 8 amps per microsecond. So that means that's pretty amazingly fast, okay? So here's the operating curve. Now, what we've got here is on the curve, you can see the voltage can go up and down. Here's the power going up, and here is the current going up. As the current goes up, it means the resistance is going down. Those are inversely proportional. And I wanted to tell you a story. I used to do some flying in a Cessna 172, just a small little plane, and I like to watch videos. And they were talking about big jetliners and how they have performance curves, and how a jetliner, you typically fly at 30,000 to 33,000 feet, but they can fly. They have a service ceiling up near maybe 40,000 feet. At 40,000 feet, you're flying right at the limits of what you can do. That would be the coffin corner right here. And in fact, the stall speed may only be 5 knots slower than your airspeed. So they fly these real high. If you go the 5 knots too slow, you get a high speed stall. You fall. Typically, it takes 10,000 feet to recover, 20,000 feet to recover. I saw a video the other day, and the co-pilot didn't understand what was going on, and he didn't realize he had a high speed stall. He's got his pitch up, and basically he ended up in a coffin, and everyone else on the plane did as well. So that's why they call that a coffin corner. Now, when you do test and measurement, if something's going to fail, it's going to probably be in one of these corners right here. So you can test, and you can test all through here, but you can probably accelerate your testing by concentrating in these particular areas where something's more likely to fail. Any questions? I see a chat. Let's see what we have. Do we have sales in Canada? Yes, we do. And Chad is our expert for Canada, and he's the right guy to contact regarding sales up in Canada. Okay. Any other questions? Okay. So moving on. This is the 6 loads that we have available. And what I wanted to point out is we have 150 volt or 500 volt. We got 125 watt, 500, and 250. But this 125 watt can handle up to 3.6 kilowatts for brief intervals. So instead of buying a 500 watt load or kilowatt load, you may find that this works for you perfectly well. Same with that 250 watt load, you may find it replaces a 2 kilowatt load. So that's, can you send us this presentation, Mark? Absolutely. In fact, we're going to send this presentation to everyone. And in fact, we've got a short video, one of the slides near the back, it says, click on this, and it'll take you over to YouTube and actually show you a presentation of the load. So we post a lot of our demos on YouTube. We also post them on our website. You can go to Vitrek.com and look under, I don't know, I forget what you look under, but it's in there. We post all these. So that's the slides, and from there, again, there's our contact information for the company and for us. And from there, I'm going to go on over and actually show you the equipment. Now, So what you'll see is, because I can remote into this load, I can run it from my web browser. All I did was I put an IP address in here. Like always, you make sure you're on the same subnet, and that's really all there is to it. It connects up, and I can blow this up, and it works really well. Now, the main menus for this. Oh, by the way, notice that our commands are LXI compliant. That shows that we're Ethernet, and that shows we have USB. This, if you see something you like, I can connect a button. Notice that if I want to run this remotely, I have to put a password in so no one can go in there and mess with your load. And that's it. I just took a screenshot of that oscilloscope right there. Okay, it's that easy. Now, your main menus are right here. So you've got results, you've got the system, and you got the DC load. So those are the things you should start with first. I like to start with the DC load. And so I'm going to start with the basics. Notice that you can have constant current, just like all the other loads out there. You can also have constant voltage, you can have constant resistance, and you can have constant watts. And with our load, you can turn them all on simultaneously. So I think of these as constraints. So for instance, if I want to constrain and make sure this never goes above 20 volts, I can put that in here. If I want to make sure the current never goes above 1 amp, I can put that there. And if I want to make sure the power never goes above 5 watts, I put that there. And that's resistance. If I want to make sure it never goes below 200 milliohms, I can put that there. So that's, I'm going to turn that off, but that gives you a feel for some very unusual capability in this load. But this is just in the basic mode. So let's go higher, load disabled. Okay, let's see. I'm sorry, wrong button. Okay, so this is the basic mode. I can also have a table here, and I can adjust, the table can be by voltage, the current by voltage. So when you get to certain voltages, you can raise or lower the load to establish a certain amount of current. Now, we can also do this over time, and then it's called an arbitrary mode, and you can put in many steps, and this is how we can do real-world simulation. For instance, a cell phone. Let's take a cell phone. When you have a cell phone, even turned off, it's if I remember right, it's still drawing current, still talking to a cell tower. You may not realize it, but it is. When you turn it on, then it starts drawing more current. And then if you do some texting or chatting or web surfing, it draws a different amount. If you call someone, it draws a different amount. So if you wanted to simulate a cell phone, we could simulate the cell phone usage for testing the batteries in cell phones. And we would use this arbitrary mode to do that. In sweep mode, we can sweep across your entire range of operation and see if there's any weak spots. We also have the ability to do, the system's designed to be used programmatically. You can control it remotely and you can program it. We have the set of commands in the manual. And so sometimes you don't want to have a technician walk over and disconnect leads or connect leads or short leads. We can do that programmatically. We can open and short. Notice that, like most loads, we have overcurrent protection and over power protection. You can program in to make sure you don't destroy your device. So that's just the capabilities. Notice that in the basic mode, actually, always we can go between two different profiles. This is the fastest way to switch back and forth. So for instance, if I want to go from load profile A, drawing 1 amp of current max, the 1 amp constraint, and I tell it to stay there for 1 millisecond, then switch over to profile B and only allow 100 microseconds. It constrains at 100 microseconds. I can also say give it a pulse, and I can turn that on. I can say give it 1,000 pulses as an example, and it will switch back and forth 1,000 times. Now, notice I said we can do this very fast. I can put this down to 20 microseconds per step, which is probably a lot faster than you need to go. But if you do need speed, we have it. Okay. So that's A and B. General setups, okay, let's take a look at general setups. We can give you change limits. So for instance, on the single edge, both for rising and falling, or I can have different controls for each. I can specify how fast things can change, either in a slew rate in amps per microsecond, or with the filter in microseconds, okay? RHF, that's another way of slowing things down. We can simulate inductance of your system. If your system has a lot of inductance, then things won't change that fast. We can slow it down to emulate that. Self-start is another one. This is designed to protect your test article to make sure that you don't damage it by shocking it with too much voltage or current. And we have all the controls for that here. So trip voltage, I'm working on semiconductors and I don't want to go above 7 volts. I can put that in there, okay? Battery, here's our battery emulation mode. So I turn on the battery emulation, this turns on the data logger, and so basically we can go in and establish a voltage threshold. For instance, on a lead acid battery, a car battery, maybe it's fully discharged at 9 volts. I can put that in here. And what it'll do is it will test that battery till it's discharged to 9 volts, and then the test is stopped. Now that is designed so that you don't destroy that battery, because if you over discharge a battery, you can damage it. And that's why that's in there. Or you can just say test it till it dies, and make that test. We're going to test for 30 minutes or an hour, 5 hours, whatever you want. You can put it in there. Measurements. This just turns on and off digits. I like to keep them all on. So that's the general. Now profiles. This is save and recall. We can save setups. That's pretty standard. This is just the local setups. On the system menu, I can save to my USB drive as an example, or remotely. And here's my controls for logging. So I can give it a file name. Notice it saves in .csv format. I can tell how often to sample, in this case 50 milliseconds. I can tell it to give it full data or truncate and cut off some of the data. Basically, this is just the more important, more interesting data, or I can save everything. I can synchronize to external events. That's one of the reasons why you have that DIO that I showed you. I can timestamp the data. I can put headings on the data. I can continuously test, or I can append. So append is when you basically you want to have one file for all of your data, and you test 10 times and it appends it each time into that single file. That's what we're doing right there. Okay, so these are the setups. This is all the DC load. Once you're done, now you're ready to do some testing. And so remember, this is designed to be run remotely. This turns on the load. Kind of think of it like connecting the load, connected or disconnected. So you can do that from your office. You can disconnect the load and stop the test. So here's our 4 meters that are built in. You notice that we're measuring the current, and we've got a 5-digit display. Here we're measuring the resistance of the load. Here we're measuring the voltage being put out. This is my power supply. I've got a DC power supply, and this is my power. Now this is the real time, and notice that I can also say, okay, only look at what happens when we're in the profile A. So we told it to put out 1 amp, limit things to 1 amp in profile A, and you can see it's doing its job. It's right on the money. And I can look at profile B, and we told it to limit at 100 milliamps, and it's right on the money there as well. Or I can, again, look at everything. This is basically the average between 1 and 100 microamps right there. Okay. And here it tells you how long you're in each of these different profiles. Okay. So that's the meters in the scope mode. You know, it's a 4-channel scope. The really nice thing about the scope, It may free up having another scope on your bench. You can put it somewhere else and not clutter up your bench. And you've already connected to it, so you don't need to double probe. When you do double probe, it loads and causes errors in your measurements. So this is really a much better way to do this. I don't know the resolution on this. I should look that up. Typically, the resolution on our devices is 22 or 24 bits, which is a lot more resolution than you'll see on an 8 or 12-bit oscilloscope from one of the major manufacturers. Now, I'm going to turn it on. I should turn it on. And what you're seeing is we are looking at the voltage, we are looking at the current, we're looking at the power, and we're looking at the resistance. This is our traces button right here. You can click on that. And what we're doing is we can set the offset. We can align the screen to the bottom, the center, or the top. And when I set it like this, what I'm saying is put 5 volts at the bottom. Okay, that's basically lowering the trace that you're seeing right there. And here's my sensitivity. I can adjust my sensitivity in voltage, current, power, or resistance. Now, I can also bring out a cursor so that I can make measurements with this. So for instance, here's my trigger point right here. I told it, I should show you this. Here is the, I told it to put the trigger position at 10%. That means what you're seeing prior to the trigger is pre-trigger information. Everything after is post-trigger information. I can adjust my bandwidth, and I can adjust my trigger and my time base. Here is my time base. I can also use the knob for adjusting that time base as well. So that's it. The scope is really nice. Like I said, if I want to screen capture that, there's my screen capture of that trace right there. The XY, if you're an old analog guy, which I am, basically we used to call that Lisa-Jus mode. And what we're doing is, I'm going to take this to fast, a little faster. We're collecting data points as to where this thing is typically operating. So right now on voltage, this is where we're voltage constrained, obviously. The power is going up and down, but the voltage is staying locked right there. And let's see. Okay, so that's Lisa-Jus mode. It basically tells you where you're hanging out in your performance curve most of the time. Here is our data logger. We've got under history, and I'm going to stop this and start this again. When you do that, it basically clears everything. So this data logger, the way it works is it's dynamically scaling from here to here. This test is like 3 seconds long at this point, and as it gets longer, you're going to see more interesting things. I can take the load and turn it off, and you'll immediately see results from this. I can turn it on, and you see it come back up. I can also come over here and I can change I can change the load here. Okay. And so you'll notice we're logging voltage, current, power, and resistance simultaneously. So as this dynamically rescales, and this is only 10 seconds across the screen now, but when you get to an hour, it's an hour across the screen, and 10 hours and a week, 10 weeks, we can make very, very long tests. And one thing about the data logger is we use a compression algorithm. We generally just don't run out of memory. There's no real limit. It just goes like forever. And the thing is, you never need to redo your test because the data is already captured in there. And so when we change things, we're just basically, like if I change that sensitivity here, the data is already in there. All we're doing is changing the display that's going on here. So that is the 4 types of results we have. And I'm going to come on over. The last thing is the system. And here's where I can actually export all of my settings. Like if I want to export the system setup, the IO, the scope capture, the LAN, I can just click all, give it a file name, and it will do that. There's also a nice self-test in here. And so if I disconnect my leads here, I can run the self-test. I like to do this. Okay, it says take the load, it shouldn't be active, and then start. And so, you start the day, you want to make sure all your test equipment's working and CAL'd and doing good. And this test only takes 15 seconds. And sometimes things go wrong and you go, gee, is my load working? Well, you can run this real quick. Actually, yesterday I was at a customer and the customer said, your device isn't working. In this case, it was a HiPod. And so we started troubleshooting. The first thing I did was run the self-test and the device was fine. And then we troubleshot it right down to his wiring. He had some problems with his wiring. So it's nice to eliminate the piece of test equipment. So that's it. I appreciate you coming. And now if you have any questions, I'd be glad to take those questions. If not, again, we're going to send everyone the presentation. And we hope you tell all of your friends about us. And we hope you give the load a try. We think this is going to work well for you in your lab. Any questions? Could you say a word about parallel units? Yes, we can run these in parallel. The thing is, in parallel, it works only in the constant current mode. So you wouldn't have those other modes that we have available. Any other questions? Okay, in that case, thank you very much. I look forward to your emails and your comments. And I hope you join us for our next webinar. Have a good day.
Hey, Glenn, thank you very much.
You're welcome.
Thanks, Glenn.